up to the ding ding dong day.
Welcome to this presentation where we discuss the relationship of art with maths and programming. Before getting into the story of the title and what prompted me to do this talk, let me first introduce myself. My name is Lakshmi Narsimhamurthy Upadhyayula. I go by Murthy, although my English friends are used to calling me Murthy or simply Mirth for reasons only they know best. I'm an MI developer at Phoenix Group, working mainly with Oracle PL/SQL, ODI, and Jira. I also do part-time work for an American client on Unreal Engine, and I also use some of my time doing illustrations and animations, looking to bring this skill in the fore and replace my day job in the future if possible. If you're thinking at this point that I'm a jack of all trades and a master of none, then you're definitely half correct. Coming back to our topic, it all started like any good story once upon a time, by which I mean a few months ago when I found my daughter Srimuki looking like this. I asked her, "Why so serious?" To which she replied, "I hate maths." My initial thought was, why hate just maths? When I was 6, I hated all the subjects. They kept me inside a room when all I wanted to do was go outside and play. Of course, I didn't say this to her. As a professional dad, it was my duty to analyze the reasons behind this problem and come up with a viable solution. So I asked her why she hated maths. She used a lot of words to describe it, but in a gist, it's the same reason pretty much everybody I know hated maths for. It's boring, it's confusing, and hard. Kids, and most adults for that matter, don't take a great deal of interest in something that doesn't look good on the eye. Look at this, for instance. I don't think many of us would use this as a wall filler. Mookie clearly doesn't get it. This, on the other hand, is a beautiful looking flower. Mookie could certainly put this one up. So it would seem like in order for Mookie to like maths, we must somehow make maths look pretty. That's my mission, maths. Hang on a minute. Isn't maths already used in art? Indeed, as far as we know, maths was being used since at least the 4th century BC by ancient Greece. Several topics such as ideal human body proportions, geometric shapes and patterns, etc., were being studied by artists for centuries. One mathematical phenomenon that we often come across in the world of art is the golden ratio. Golden ratio, also known as extreme and mean ratio and the divine proportion, is calculated by adding two numbers and dividing the result with the larger of the two numbers, and if the result is equal to the ratio of the larger to the smaller number, and if that value comes to approximately 1.618, then it is said to be the golden ratio, denoted by the Greek symbol phi. This ratio has a close relationship with another mathematical concept called the Fibonacci sequence. The table shows how eventually the Fibonacci numbers attain this golden ratio. So, what is so golden about this ratio anyway? Here is another example of how Fibonacci numbers and golden ratio are used in geometry by the logarithmic spiral. Artists will recognize the spiral, which is often used as a guide when composing a piece of art or photography. We can see already how the arrangement of these Fibonacci squares within the outer rectangle successfully draws our eyes towards the center of that spiral. If this isn't mesmerizing enough, we can always look at some classic old school paintings to see if we can pick this log curve in them. Da Vinci's Annunciation is a great example of the use of the golden spiral, as well as linear perspective, another mathematical concept that is used to give depth to 2D images using vanishing points. You can see how the main characters and objects conform to this spiral. Here's another classic example where the golden ratio is visible on this wave. And here's another composition. And this. The artist clearly wants to draw our eyes to the pearl earring, and the way the head is positioned on the canvas and the placement of the ring allows for this. The fascinating thing about this is it is not clear whether it's the golden ratio that's enabling the artist to make us fall in love with these masterpieces, or if we are not naturally drawn to somehow follow the rules of maths without us noticing it. Here's another classic. People often talk about Mona Lisa's smile. It's clearly what Da Vinci wanted to highlight in this portrait, and clearly the proportions of the face to the smile conform to that golden spiral. The rule of third is another concept that comes up a lot in the world of art and photography. The idea is to split the canvas into 3x3 boxes and use those intersection points to place the key subjects of your artwork. You can tell that the artist here intentionally placed that house on the bottom left point. Without that precise placement, this composition wouldn't work so well. Here, the artist used 2 points to have his hero objects, and once again it works so well. Moving this slightly away from these points would definitely break this composition. While we've seen all of these visual art examples, it would be unfair to ignore other forms of art where maths is used. That's my mom playing a veena. She's a classic Carnatic musician. Carnatic music is a system of ragam, talam and layam based on different mathematical rules, as you can see on the slide. Sticking to these rules result in a pleasing musical composition, and breaking the rules simply breaks the music. Going back to our flower and knowing what we know now, it's not too far-fetched to call this "what a beautiful piece of maths" instead of "what a beautiful piece of painting." All I have to do now is to prove to my daughter that maths is indeed beautiful, and maybe I have a chance to change her opinion about it. For my demo project, I chose the concept of phyllotaxis. It's a botanical pattern found all over nature, and it uses the golden ratio in its own way to produce this peculiar yet beautiful spiral pattern. And to visualize this, I will be using Blender, which, for those who are unaware, is a 3D software used in a multitude of applications such as games, VFX, music videos, and so on. This slide goes over the logic behind phyllotaxis. We will be using polar coordinates, which means we will plot some points on a graph based on the x and y Cartesian values calculated using the formulas shown on this slide. When r and theta from the above equation are constants, we get a circle, which itself is pretty fascinating. But if we swap the values of r and theta with another equation as shown in the bottom image, we will get different values for each of the points, helping us to plot them in a phyllotaxis pattern. The key to this is that golden angle. This is the pseudocode that we will try to execute. There are many ways in which we can demonstrate this, but my choice is to use Blender's geometry nodes to help us visualize this. The for loop is where all the logic really resides, as we are calculating the x and y Cartesian coordinates and applying them to the points. We first define the number of points with the variable n, and then c, which is a scaling factor, determines how large or small our phyllotaxis is going to look on the screen. There are many interfaces in Blender depending on what task you're looking to achieve, but we are interested in the geometry nodes. The UI is as shown here. On the left, we have a spreadsheet with location of points of the selected cube in the viewport. On the right, we have the outliner showing the objects within the scene, and under that we have the modifier stack, which is used to modify the geometry based on the function of the selected modifier. Right at the bottom is where we have the geometry nodes area, which is used to define custom logic for modifying the geometry. In a nutshell, geometry nodes takes the data of the selected object, manipulates that data, and outputs the modified data, which is applied back to the selected geometry. This is the visual code version of the pseudocode that we saw earlier. We define our variables and then connect these with a few nodes, as you can see above. The blue nodes are the inbuilt math functions inside Blender. These are used to get the multiply, cosine, and the sine functions to calculate the x and y positions. As we need a number of points to iterate over, and Blender doesn't provide us a default node to create a point, or a for loop for that matter, we will have to use the mesh line node, which comes with the defined number of points stacked vertically as shown here. Now that we have the x and y position data and the points through the mesh line node, we need to manipulate the position of the points using these calculated values and inputting it to the set position node. Of course, we need to first convert the scalar x and y values to a vector before doing this, as 3D manipulation requires vector maths to know the direction of the movements. This is the result, and you can see it does follow the pattern that we set out to achieve. Since we were providing the exact golden angle to achieve this, I got a little curious and changed this value to other values, as you can see here. Here I'm using the scene time node for the angle, which ticks over every second to give us an animation like this. Adding some shading and attaching a music waveform to the scale values, as you can see, will give me this audio visualizer effect. Now we're getting somewhere. This looks like the sort of thing that my daughter will appreciate, and that means we have a chance to win her over and make her like maths. To take it to the next level, I thought of compositing the result behind this young lady and see if that would give the maximum impact. I mean, why not?
Boing, boom, chuck. Boing, boom, chuck. Boing, boom, chuck. Boing, ping, boom, chuck, ping. 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 Boing, ping, boom, chuck, ping.
With this result looking pretty convincing, I invited my daughter to take a look. As expected, she was blown away. She really wanted to learn it all. Trying hard to hide my smugness, I asked her to meet me in the living room in 5 minutes. In the living room, I would set up my laptop and some basic maths lessons and coding lessons ready for her with a cool project idea. She would eventually come all dressed up and pretty. I thought this is how kids nowadays turn up to maths lessons. What do I know? As I was getting ready to execute my successful plan, she would take my phone, open the camera, and click record and hand the phone back to me. It was at this point that reality hit me like a hard red brick when I realized that my daughter was really interested and got all excited about the music and the dance, but none of the art that I worked so hard in creating. Alas, while this didn't go exactly as planned, I hope that it provided some food for thought and made an interesting presentation for all of you. If you would like to try out other patterns using geometry nodes, I suggest playing with Desmos first. Desmos is a polar coordinates playground which allows you to put some equations and see the output in real time, as you can see here. I especially like that last equation. While this whole thing didn't go to plan with my daughter, I do hope that it served its purpose in exciting all of you to the concept of using maths and code to create art. Thank you for watching. I would like to take this opportunity to thank the DDD Southwest organizers and the audience who turned up to that event. You will always be special for me, as this was my first ever talk at a conference and your engagement made it a success. That's it from me for this video. If you're curious about how I created my daughter's caricatures, you may want to subscribe to this channel and hit the bell icon, as that's coming up next.